Okay, so we are continuing our discussion on random variables. In this video, I'm talking about uniform random variables and then exponential. So a uniform random variable is defined as a random variable that has the same probability for each possible value, right? So same probability for each possible outcome. Okay, so this is similar to what we've been talking about uniform probability space that has the same probability for each outcome, right? So if there are n possible values, we may assume that there are 1, 2, 3 up to n, each with probability 1 to n. For example, rolling of a fair die, right? So if we think about the rolling of a fair die, it's a uniform random variable with n equals 6 because we have 6 possible values. And if x is the random variable that is defined as uniform on n values, this means its PDF is given by k for all values of k equals probability of x. This is how we denote it, is going to be 1 over n for k equals 1, 2, and so on up to n. Now there is another way of denoting this. It's also called the shorthand. So for example, I can say x and then this small sign tilde and then uniform n, which means x is uniform on 1 up to n, right? We can also verify that the sum of the PDF, like n terms each, is equal to 1 over n, and so the sum of the PDFs is 1. So that it should be valid for all PDFs. Okay, so this is simple. Yeah, and one more thing, if we go and plot the uniform distribution, it usually looks like, and this is also, that's why called a rectangular distribution. So it usually looks something like this because this is going to be my PDF, and this is all possible values of x or k, however you want to call it, and each will have like an exact same probability. For example, in our die example, this is 1/6, right? For every possible, getting 1, 2, 3, 4, 5, 6. Right, so it's also called uniform or rectangular distribution. Okay, so let's look at another random variable, that's the exponential. This is also referred to as something that relates waiting time to success, right? Okay, or to put it in different words, this actually represents how many trials do we need until we succeed, right? So one common approach is that like we make independent attempts at some task with some success probability that is known to us and then stop when we succeed, right? Okay, so let's write down a few things. Let me again assume x is the number of attempts you make. This is my random variable, number of attempts that you make, right? And now let's compute the probability of x such that I know that in each attempt I have an equal chance of, or not an equal chance, but my success probability is known. Right, so that success probability is p, so obviously my failure probability is 1 minus p. Now let's think about flipping the coin example. So if I get a heads, I'm considering that as a success, and if I get a tails, I'm considering that as a failure. And let's try the outcome tree method to visualize this experiment. So essentially, as long as I do not get a heads, I need to keep flipping the coin, right? So like we remember from the outcome tree method, this is my try one. So I can either get a failure or I can get a success. So this could be any generic experiment. The probability of success, as I stated here, is p. So the probability, so this is the edge probability, and then 1 minus p for failure. So if I get a success, And these are something called waiting times. So instead of outcomes, we are writing waiting times. These are discrete waiting times. Right, so this actually relates to how many tries, right? So in one try, I got success. Let's say I did not get success, so I have to try again. I can get a failure with, again, probability 1 minus p, but I can get a success with probability p. My waiting time here is going to be 2. And I can also keep writing the probabilities given that I'm assuming these are independent trials. So this is p. This is going to be p times 1 minus p, because this was 1 minus p here, and then times p to arrive here. Again, try 3, I can get failure, success, 1 minus p, p, waiting time 3, p times 1 minus p square, and so on. Right, so in general, if the waiting time is t, such that the first t minus 1 trials fail, then the tth one succeeds, right? So if I'm denoting these waiting times by t, this is what it means, right? And so because trials are independent, so for this experiment, I can write the distribution function for x, which is the number of attempts, uh, over this waiting time t as 1 minus p t minus 1 times p, right? A more convenient way of writing this expression is like this. We use a term called beta, and then 1 minus p to the t, where beta is nothing but p 1 minus p, right? Or to write it more formally, this is beta 1 minus p to the t for t equals 1, 2, 3, and so on until I get success, right? So this is also called the exponential random variable, and it's pretty easy to visualize this because, as you can see here, as the waiting time is increasing, my probability distribution function for a given value of t is diminishing, right? So this is the common um, this is a very frequently used distribution for problems that relate to waiting times, that relate to success trials or trials until success type of problems. Here I can plot the probability distribution function and time, and this is usually, it begins with a higher value for given value of like 0, 1, 2, and so on, and it diminishes like this. So it'll diminish up like at some point. This is how the probability distribution function graph looks like for this distribution. Okay, for some of the examples, for example, where we can actually see the exponential distribution is, for example, your router trying to send an internet packet until it's received, or millions of people trying to access the Google server, and so on, right? So we are essentially trying to answer the question, how many trials do we need to get success? Okay then, so with this example, I end this video.